All right, so you need to get out your packet, atomic structure bellwork number 4, and your periodic table.
That's all atomic structure.
Atomic structure is really fun.
Love the math.
It's good. It's easy math. It's capable, you know, and makes sense. I think it's great stuff. All right. I'm going to take a little attendance. We'll check it again in a second. I'll see if you guys have any questions, but we'll give them one more moment to make it in. One, two, three, 4, 5. 1, 2, 3, 4, 5. All right. Well, we'll just get started, and if people come on in, then we will get them caught up as they come in. But let's get it started so we can get everything done and then get you on to your next class. Do you guys have a lot of classes this morning? I heard that there's some other teachers doing some live classes today too. So perfect. Oh, yay, we have another person. We'll put this here. We should have 6 now. All right. All right. So here we go. The first thing I want to do, you guys probably have the bellwork in front of you. But what I would like to do first is I would like to make sure and see if anybody has any questions before we get started on anything we've been doing so far. All right. So perfect. So hopefully you guys have watched all 4 lectures. So let's make sure we understand what that means when we go through. So on the week of last week, there was a lecture in Monday and Tuesday. Those are closed. So if you have not done them, but you need to do them, meet up with me or email me and we can make some time to get you to do that. And then there were 2 lectures this week as well. So if you are kind of keeping up where we're at, we're on the 2nd right here, Wednesday the 2nd. We are going to do what's called History of the Atoms Notes number 5. This was a little more challenging. So that's why we wanted to do it kind of live with you guys. We found out really late last night you guys will be coming back starting Monday. Cohort A will be in, and then the next Monday, Cohort B will be in. So we each get 1 more week. So we can practice all this stuff. You guys next week, at the end of the week, have a unit test over everything. And what that means is that's always from atomic structure, atoms, ions, isotopes, what are they, cations, anions, all of that stuff through all of the history of the atom. So again, you should have watched lecture number 1, number 2. And then this week, you should have watched lecture number 3 and number 4. If you have any questions, I can talk to you one-on-one about if you are missing anything. I have it kind of written down from when I checked this morning. But you need to make sure you know all this stuff because, per usual, we do have a quiz on this at the end of the week on Friday. So get in there if you've watched all 4 lectures. There is also a lab that is posted. Half of you have done the lab. It's called the flame test lab, but I would still watch it because you never did the post lab question. So if you did the flame test lab and you got the front done, go ahead and watch the lab and you want to do the back. So in this week, week 15, okay, there is the Thursday flame test lab. So you do want to go in. There is a question off of this lab on the quiz on Friday. Okay. And then participation points, we'll put those in at some point in time. They just look a little bit different. You guys are all going to write A, that you were here, and you got your participation points. So let's talk about the quiz. On Friday, this Friday, 2 days from now, it's going to be open between 7:30 and 1:30 per usual. Now, it's only 5 questions, and people are like, what? And it's 31 points. So the things it's going to be is it's going to be an atomic structure chart that we're going to practice right now. It is also going to be all the scientists and what they did. So you do have to know the scientists. You have to have watched the 4 lectures coming up to this, and you have to know all the scientists. It talked about how an atom emits light, which was Monday's lecture, and we go over it a whole lot more in Thursday's lab. So you want to make sure you watch the lab and Thursday folder. And then orbital charts, which we're learning today. And then there is a question from the lab. You'll have to tell me one of the colors of one of the elements. So you want to make sure you watch the lab as well. So please notice that I said it's 5 questions. And here's 1, 2, 3, 4, 5 things that you need to know. So you can deduce from there what the questions are going to be over. So I'm telling you, it's 5 questions, 31 points. This Friday is open from 7, I think it's even 7 o'clock if you want to wake up early, and till 1:30, and then it will close. The other thing that I want to point out, though, for 5 questions, I'm giving you 45 minutes. So that's a lot of time. But you will only get 45 minutes. So you have to know the scientists. You have to know what they're doing. If you think you're going to get in there and just look it up as you go along, you will run out of time. So 45 minutes is ample time. I think it should take the well-prepared student 10 minutes. So if you know what you're doing, you know the scientists, you've seen all the lectures, should be a piece of cake. But if you haven't, you want to make sure that you do that before you start the quiz. Okay? So that's just kind of a little disclaimer before you start the quiz on Friday. Okay? Does anybody have any questions on that? Awesome. All right, so I got a little joke here. It has this little guy. He says, electron is proton. Where are you? And the electron says, ooh, that's a toughie. I can tell you where I probably am. Does that help? Because on the lecture from yesterday, when we got into quantum mechanics, we were talking about how Bohr is wrong. You can't tell exactly where an electron is. You just have to use probability to tell me where it might be. Okay, so first thing we're going to do, we're going to get into here, is we are going to have you guys get out your periodic table. I wrote this one right here, the 4th one down, to be kind of tricky. So make sure you take a look at that one. If you don't know the atomic number and you don't know the element, but you know the mass and you know the number of neutrons, can you calculate the number of protons? So that's kind of a question there. So we're going to have you guys do this bell work. I'll probably give about 4 or 5 minutes to have you guys do some of this. If you need a refresher, remember the atomic number always tells you the number of protons. It also tells you what the element is. The mass number is made of the 2 things that have mass are protons and neutrons. And then when you're looking at charge, you look at the 2 things that have charge, which are protons, which are positive, and electrons, which are negative. Okay. So remember, you'll go through and you'll just say nickel, find him on the periodic table. Tell me his atomic number. That's also the number of protons. If you have protons and mass, you just subtract them for neutrons. And then if I have 26 minuses and however many pluses I have, what is that charge? And then I want you to use yesterday's notes and tell me the 3 answers to the questions on the back. Okay? So why don't you take a moment or two. I want to put the music on quietly. I'm probably going to just call you out to see if you have any questions throughout the week. Just check in, hear your voice, and then I'll give you your points for today. So you guys are working on that. Okay, let's do like the first one. So you looked up nickel and you saw that he has 28 protons, right? So we're going to put 28 for atomic number and protons. The number of neutrons, remember, the only things that have mass in the atom are protons have a mass of 1 and neutrons have a mass of 1. So these 2 numbers have to add up to the mass number. So 28 plus what will give me the mass number. So what you do is you just subtract mass number and number of protons, or you can remember it is just A minus Z as well. So 59 minus 28 is going to give me 31 neutrons. Okay.
Okay, and I'm kind of confused as to find the charge.
Perfect. So let's do another one. So the only 2 things that have charge are the protons, which are positive, and the electrons, which are negative. So what you're going to see is if I have 28 plus minus 26, which one do I have more of?
The protons.
So I'm going to be positive by how many more do I have?
2.
Perfect.
Okay.
Now on this one down here, I want to be a negative 4. So I just simply got this number. Where did I get that 14 from? Atomic number tells me the number of protons. So I have 14 pluses. How many minuses do I need to get to negative 4?
I put negative 10, but that's probably not right.
Okay, so 10, if I had 10 negatives, that's going to give me to positive 4.
Yeah.
But I want an extra 4 of these guys over here. So what is 4 more than 14?
Is it 18?
You got it. So now I'm plus 14 minus 18. I have more electrons by 4. Okay?
Okay. Thank
Perfect.
you.
Thank you for asking. Very good. All right, so let's see. Stop my music. Let's go here. Let's see how you did. The next one, atomic number 14, tells me that it's silicone. I have 14 protons and 16 neutrons. So my atomic number is 30. My mass number, is 30. The next one, I look up iron. You can see it has 26 protons, the atomic number. And then I do 29 plus 26 gives me an atomic mass of 55. Now, if you put 56, because you just pulled it off the periodic table, that is one of the isotopes. But you don't just write down what you see off of here. Because you were given the number of neutrons, okay, because you got the number of neutrons and the number of protons, you need to add those together to get your mass number. Okay, you don't just assume it's the one off the periodic table unless that's the only option you have. Then let's talk charge. You see that I have 20, get a pen here. I have 26 pluses, 23 minuses. So that means I'm more pluses by the number of 3. Very good. Now this one I said was promised a little bit harder here. You have the mass, which it can be 2 different things if you were looking at the periodic table. So let's do this. We're going to say 15 minus 31 is going to give me an atomic number and a number of protons of 16. Once you know that it's 16, then you can go ahead and tell me that that is sulfur. Okay. Awesome. So then the last one we have is bromine. You look it up. It has 35 protons. The next one, if I want to be negative by 1, that means I need an extra negative electron. Oh, I forgot to do the electrons on sulfur. I saw somebody else come in and I got excited. Sorry. Then we have here, you have 35, 36. This gets me negative by 1. And then if we're trying to find neutrons, we say, all right, my mass number is 80. 35 minus 80 gives me a mass of 45. And then, yeah, let me go back up here. 16 pluses. I want to be negative by 2. So that means I need 2 extra negatives. So how many negatives should I have here? I would have 18. Okay, perfect. So hopefully you guys feel good with the top. Hopefully we don't have any questions. If you're coming in late, we're working on atomic structure bell work number 4. If you want to hang around at the end, I can talk to you about, we talked about the quiz and stuff like that and kind of the agenda. So if you would like to hang around afterwards, I can run that down with you as well. So on the back, we are now talking about quantum mechanics. So we have extended the idea of Bohr, and he wasn't exactly right. And then quantum mechanics is what we know now today as our working model. Okay, so is an electron a particle, a wave? And de Broglie said it can be both, which is the wave duality of nature, a wave-particle duality of nature. And it's weird that an electron can be both a wave and a particle at the same time, but that's kind of the model we're operating under right now. Heisenberg's uncertainty principle, and these are all from yesterday's notes, says it's impossible to know the location and the movement of an electron at the same time. So you can either see where it is and not know where it's going, or you can get a general vicinity of where it's going and not know where it is. But you can't know them both at the same time. So electrons are notoriously hard to track down. We don't know exactly where they are around the nucleus. And that's kind of what we're working on currently. Some of the particle physics is what's going on right now. The last question there is, what is an orbital? And so because we don't know exactly where it is with Schrodinger's mathematical equation, he said you can't know where it is. So we said an orbital is a region of space where there is a high probability of finding an electron. It's not necessarily exact science. Okay, they're so small you can't really see exactly where they are, but we have found them in locations with math, and then you put it together and make a probable space where they are. Now, each orbital can hold 0, 1, or 2 electrons. And what we're going to do today is we're going to talk a whole lot more about orbitals, what shapes they are, all that kind of good stuff. And it gets a little bit more like mind numbing because it's very hard to understand. This is why you learn this in chemistry. You don't learn this in physical science. This is tough stuff. Okay. So go ahead and get out your periodic table here, and then turn to page History of the Atoms Notes Part 5. So hopefully we're doing good with this. I have this is going to help me show one thing. All right. So the first thing we're going to talk about is that Bohr was mostly correct. Bohr just couldn't see in. He didn't have some of the technologies we have today. So what he didn't see is that each of his orbits, remember what Bohr said? Bohr said that electrons, they're in these predictable little paths that go around the nucleus like planets around the sun. What he didn't see is that each of those little paths, okay, were broken down into smaller regions called orbitals. Okay, and again, an orbital is just a space around the nucleus that can hold 0, 1, or 2 electrons. However, what Bohr was right about, and what we're not going to change about the Bohr model, is that it takes a low amount of energy to reside closer to the nucleus, and it takes a higher amount of energy to reside further away from the nucleus. So he was absolutely correct with that the electrons want to stay closer to the nucleus because it's a lower amount of energy. Okay. Awesome. So moving on, let's talk about what an orbital is. And I have a little video here that kind of shows how they came up with these because it's all about probability. So let me see if I can't get you guys to hear this. I'm going to turn this up.
For a day, a week.
All right. So what they're going to do is they're going to show you they used math to figure out where an electron is at one point in time, and then they plot it all together. And when they plot it all together, that's when you can eventually create a shape of where it's most, it's like the bee in the beehive. If you took a picture of a bee and it was here and it was here and it was here and it was here, and eventually over days, if you overlap all those pictures of the bee, you can see where the bee normally hangs out. Okay, so this is kind of just a little video showing that.
For a day, a week, and a manner with fixed energy around the nucleus, and then imagine that we take a picture of this electron every second for a day, a week, or month. We see that all these pictures laid on top of one another begin to form an electron cloud around the nucleus. Remember, all these hypothetical pictures or data points represent where the electron has been over time. If we now attempt to create a three-dimensional surface to encompass 90% of all these data points, we obtain a sphere, which is often called the boundary surface.
All right. So basically what they're saying and what we're about to show you right now is the shapes of these orbitals, or where there's a high probability of finding the electrons. And you can kind of see them back here behind me. They look kind of weird, and you're wondering how do they know that this is where an electron might be? And they've done it by taking probability and overlapping it over time. And then they say this is where it's likely to find an electron. Okay. So there are 4 different orbital types, and then they all have a different amount of variety. So on your little chart here, let's write this down. The first orbital type is called an s orbital, and that's the one that I'm holding right here. And there's only one variety of it. And you can either say draw a little circle, or sometimes I write that it looks like a sphere. Okay. But so again, at the intersection of these little tines on all of these is where the nucleus is, right at the intersection. And this kind of ball around here is where there's a high probability of finding an electron in an S shape. Then there's another shape. The next shape is called the P shape, P-shaped orbitals. And there are actually 3 P-shaped orbitals, 1, 2, and 3. And you might be like, silly Mrs. Bay, you bought 2 of the same thing, but that, nope, this one goes in and out on the Z-axis. This goes on the X-axis. And then this one goes on the Y-axis. So there are 3 varieties of the P. As we're giving away answers now on this one. Silly smartboard. And I think that they look like a pair. So P for pear shape, or pair of them together is kind of how I remember it. P. Okay. Maybe we go like this. Wonderful. Okay. So there's 3. This is, again, where the nucleus is, right where these tongs meet. And these are just regions of space around the electron where there is a high, around the nucleus, where there is a high probability of finding an electron. The next shape that they calculated mathematically is called the d orbital. There are 5 varieties of that one. They get kind of crazy. You have the lobes that go on the x-axis, on the y-axis, on the z-axis. Okay, and then you have another really weird one that looks like this. Again, these are just where over time they've taken pictures and they know that the electron has a high probability of being in that area. So I call them daisies. That's how I remember. I think it looks like a little lobed flower. So if you want to write daisy, I-S, what? Okay, so the electron can be anywhere in this shape. That's where the highest probability is finding an electron in that shape. And then the last one are called the F orbitals. The F have 7 different varieties. We do not actually have the models because for some reason these things are like 30 bucks a pop and we couldn't really justify buying 7 of those when you can just take a look at the picture. They're pretty much what I would call like 2 sets of the Ds put together. Okay, so you have your daisy. It's in 2 sets here. You have this weird one. It's just doubled the Ds, if you will. Okay, so again, what you're looking at are just regions of space, and the yellow and the red don't mean anything different to us. They're just quantum spin, which we're not learning about. But so these are just regions of space around the nucleus where there's a high probability of finding an electron. Okay, all right, so now let's put it all together with orbits and orbitals and all of this kind of business, and then we'll show you the new atomic model. Okay, so what Bohr didn't know was that each of his little orbits was an energy level. And in each of those energy levels, a couple of different things are going on. So we're going to talk about energy levels 1 through 4. Okay, and there is a whole bunch of answers. 1 through 4. I don't know why my smartboard does this sometimes. I'm sorry. So energy level 1 through 4, and there it goes again. Wonderful. Okay. Energy level 1 is closest to the nucleus. Energy level 2 is a little further away. 3 and energy level 4 is the farthest. So if I could kind of take a microscope and look in energy level 1, you would see one orbital type. It would just have an S-shaped orbital in energy level 1. Okay. And remember, each of these can hold 0, 1, or 2 electrons. And this is why Bohr's model worked well for hydrogen and helium, which were very easy, simple little atoms, because this looks almost like an orbit. Okay, because in the first energy level, there is simply an S shape, and that there's only one type of it, so we're going to put a 1 there. What I have here is a little bit of a video. Slide this in here. So right at the intersection of the blue and the red and the green is where the nucleus is. And in the first energy level, you have a possibility of finding 0, 1, or 2 electrons just in this shape. Okay, awesome. Then, make this one. In the second energy level, so a little bit further out here in the second energy level, you actually have 2 shapes. You have S and P shapes. So we have S, then if I could overlap this, 3 different P shapes in the second energy level. So that means you have 1 S and 3 P, so the total different varieties happens to be 4. So with my little video here, on the next energy level, there's an S-shaped orbital. Remember, this is just a region of space where there is a high probability of finding an electron. Let me go back here. Okay, so that's first energy level has an S. Second energy level has an S, and it has 3 Ps. This is where you might find 0, 1, or 2 electrons. This might be where you find 0, 1, or 2 electrons, and you might find 0, 1, or 2 electrons around here as well. Nice. Then, and you might start to see a pattern, in energy level 3, you have S shapes, P shapes, and D shapes. But it gets a little weird here because science just always has to be weird. So you have 1 S, 3 Ps, and 5 Ds. So that's a total of 9. possible orbitals in the third energy level. So again, in the third energy level, we have another S shape. Third energy level has another S shape, another set of P shapes, and then it's actually going to have the D shapes, but we'll get there in a second because there's something weird that happens next. In the fourth energy level, you have, you probably guessed it, the S shape, the P shape, the D shape, and the F shapes. And so 1, 3, 5, and 7 actually gives you 16 different orbitals in that energy level. Okay. So you guys have maybe heard of this before. So we're going to fill in this last chart portion right here. I've been ignoring that on purpose because you guys might have seen these numbers before. So how many electrons can fit in the first energy level? If the energy level number 1 only has one S shape, remember you can have 0, 1, or 2 electrons in each orbital. 2 times 1, you can only fit 2 electrons in the first energy level. In the second energy level, okay, 2 times, I can put 2 in each of 4. That means I'll have 8, a possible of 8 electrons in every second energy level. Then 9 times 2, I can fit 18 electrons in the third energy level. And then 16 times 2, I can fit 32 electrons in each of the fourth energy level. So I can only fit 2 electrons in the first energy level. I can fit 8 electrons in the second energy level. I can fit 18 in the third energy level, and I can fit 32 in the fourth energy level. So that's how many electrons you can have in each of the energy levels around the nucleus. Okay, perfect. So as you guys see that this thing is getting kind of crazy with all this random, and there's some, and so there's no way you could possibly draw this. This is a very confusing model. So what they did was they made what's called an orbital chart. So this is our new model here. It's called an orbital chart. Just to get your bearings on this, right down here is where the nucleus is. And you can see energy level 1, 2, 3, 4, it keeps going. Okay, so this is moving away from the nucleus. So this would need a high amount of energy. And this is a low amount of energy being closer to the nucleus. The little bubbles that you see on each of these are simply representing the orbitals. And when you're going to put an electron in there, you're going to just use a slash. Okay. Now, there are 2 scientists that worked to develop this, and they each made their own rule or principle to tell us how to use these. The first one, his name is Aufbau, and he wrote the Aufbau principle. And he said that what Bohr said was correct, and that electrons want to be in the lowest energy state possible. So electrons fill from the lowest energy, and they fill up from there. So when you start putting your electrons in here, you're going to start putting slashes. You're not like, woo, I'm going to put my electrons way up here, because you always start putting your electrons in closest to the nucleus. Aufbau's principle says that electrons like, and that's what ground state is, which is nice. Okay, so all electrons want to be as low and as close to the nucleus as possible. There is one caveat, because there always is in science. You see energy level 1, if you can look up at this chart, energy level 1 should just have an S. So we see energy level just has one, just has an S. Energy level 2 has an S and a P shape. So energy level 2 has an S and a P shape. Energy level 3 has S, P, and D shapes. Now check this out though. Energy level 3 has S, P, and D shapes, but look at this 4S. He happens to be closer to the nucleus. Let's talk about why. When you're looking geometrically, what would give you a closer path to the nucleus? This sphere just happens to have the electrons be able to be closer to the nucleus than these lobes on this D shape. So what is actually going to happen is the energy level 4S will fill in before 3D shapes. So if that's hard to understand and you're like, I don't even know that, then just go by what this chart tells you. So it tells you when you're going along, you fill up 1S, 2s, 2p, 3s, 3p. Then you fill up the next one that's closest to the bottom is 4s, and then 3d. Okay, so when you're filling this, you always choose the one that's closest to the nucleus as it can be. But the other half of the rule is that electrons are negative, okay? And so they don't like to be near each other because you know that opposites attract and likes repel. So the other scientist and the last scientist you need to know, his name is Hund. And he had a rule that you may only put one electron in each orbital before doubling up. And you know that an orbital has a maximum of 0, 1, or can't have any more than 2 electrons in each orbital. Okay? All right, so let's put this all together, shall we? So here we go. So just on the back of your page here, we should be good. This is orbital charts practice. The first thing you're going to do is you're going to look at what element it gives you. So we're looking at neon. So I find my periodic table. I look at neon. I see that he has 10 for his atomic number. It has a neutral charge. So if it's positive 10, it'll also be negative 10 in order to be neutral. So what you're going to do when you fill an orbital, and I'm kind of looking at these rules down here, you go all the same direction and you fill from left to right. So I need a slash. And so you just follow along with me and eventually you'll figure it out. We have 10 electrons. I'm going to start by alpha tells me to put it at the bottom. 1 electron. 2 electrons. I can only fit 2 in a bubble, then I got to go. 3 electrons. 4 electrons. Now, Hunt says they don't want to be together if they don't have to. So I'm going to go 5, 6, 7. Then if you have to go back, you double A up 8, 9, 10. Okay. Let's try iron over here. If you look up iron on your periodic table, you'll see that he has 26 electrons when he's neutral. So let's do that again. We always start at the bottom. You give them their own orbital until they have to double up, and then you can only fit 2. So let's do 26. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, give them their own, 16, 17, 18, 19, 20. We're going to do 4s before we do 3d. Now I need to find, because I'm at 20, a spot for 6 more electrons. 1, 2, 3, 4, 5. Spread them out, because that's what Hund's rule says. And then we go back, boom, then we can double up for 26. Now I have 26 slashes. So let's talk about what you've just done. You have just used your slashes to tell me how many electrons are in each shape around the nucleus and what energy level. So the last thing we have to learn is how to write what's called the electron configuration, because the chart is nice to look at, but it can get kind of confusing. So what they did was they made a notation for you to write down what you put in the chart. The energy level is a big number. You lowercase the orbital letter, and then you superscript the number of electrons. So let's see what that means. In a few examples, you'll get it. So what we're going to do is I'm going to start reading from the bottom up. The first place I put electrons here, I'm going to do this neon side, is I put them in 1s. And how many electrons do I have in there? I have 2. So I'm going to write 1 really big. Then I'm going to write S is the shape I filled first, and it has 2 slashes in it. Oh, heavens. I swear. And then I write the next one is 2S has 2. So again, I am just following up here. 1S has 2, 2S has 2, and then 2P has 6 slashes in it, 2, 4, 6. So you're just telling me in the first energy level, there's 2 electrons in this shape. In the second energy level, there's 2 electrons in this shape. And in the third energy level, you have 6 electrons because you have 2 electrons in each of these shapes. Okay. Let's do iron. Iron, 1s has 2 electrons. 2s has 2 electrons. Again, I'm just reading up. 2p has 6 electrons. Now I'm going to go to 3s has 2 electrons. Then I'm just reading along. 3p has 6 electrons. 4s has 2. You put 4s in next just because it happens to be closer to the nucleus. Then 3d, how many electrons are in here? 1, 2, 3, 4, 5, 6. So you're just writing down what you've already filled in. So it shouldn't be super hard. Once you fill it in, you just write the energy level, the shape, and how many slashes you have in there. I'm going to save the bottom of this for when you guys come in. So what I want you to do is turn the page in the last 2 minutes here. And I have this, there is one of these on the quiz on Friday, and I have this key online. What you're going to do here is I'm giving away answers. You're going to look at argon. When I look at argon, I see that he has an atomic number of 18. So that means that he would also have 18 electrons. 18. These are all going to be neutral, so the 2 numbers will be the same for right now. Let's do this. Ready? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So to write the electron configuration, all I have to do is I just have to write 1s has 2, 2s has 2, 2p has 6, 3s has 2, and 3p has 6. Okay. Sulfur, if you look him up, he has 16 electrons. 1, 2, 3, 4, 5. Oh, goodness gracious. Look at me breaking Hund's rule already. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so when you're done with him, you write 1s2, 2s2, 2p6, 3s2, but 3p has 4 electrons in it. Okay, so you're just writing what you have filled in. 1s has 2, 2s has 2, 2p has 6, 3s has 2, 3p has 4 electrons. Each electron is a slash. The 2 main rules you want to remember is Alpha says you have to start at the bottom. You can't be like, you know what I like? I like 4D. We're going to put it right up there. And then Hund's rule says you want to give them their own spaces until they have to double up, and you can't put any more than 2. Okay, so my suggestion is before your quiz on Friday is finish this practice chart. The key is in the Wednesday folder here. I also put the key to the bell work, even though we went over all that. But if you weren't here for that, the key is in there. And then here is practice number 1 key. I would suggest doing that before your quiz. And then make sure you watch the lab for Thursday. And then take the quiz on Friday. Whoa, perfect timing. Man, it's like I planned that. So if you guys have any questions, please stick around. If not, make sure you watched all 4 lectures, watch Thursday, and then take the quiz on Friday. And I will see cohort A back on Monday. Thank you, guys. Have a great day. If you came in late and I didn't get your attendance, hang around. But if you did, enjoy.